we're going to begin discussing what antiderivatives are. And a simple way of thinking about them, at least to get started, is that it is the reverse process of taking the derivative. So you know that if you have a function like x squared, its derivative is f prime of x. And so if we were asking you to find the antiderivative of 2x, the answer would be x squared. But there's a problem, and one issue is to notice that if you had a slightly different function, like x squared plus 3, its derivative would also be 2x. And broadly, any function, x squared plus some constant, would always result in a derivative of 2x. Right? So graphically, this is getting at an idea that this parabola has 2x as its derivative, and so does this parabola, and so does this parabola, and so does this one, so on and so forth. And so one of the issues is trying to figure out which specific function we're originally talking about. But at least for now, we're going to address the problem by saying that we know that it will vary by a constant. So the antiderivative of 2x is equal to x squared plus some constant. At this point, we will not be able to identify what the constant is without some more information. Now, another term for finding the antiderivative is this idea of finding the integral. And the notation for finding the integral of something, if I wanted to find the integral of x squared, would be using this symbol, which we'll go into a little more detail about in the future. What is the integral of x squared with respect to x? And what this is telling you, in one sense, is that, let me change this for a second. What is the integral of 2x dx? Is that 2x is the derivative of something, and it came from taking the derivative with respect to x. What was that thing? So I know that I would be reversing the power rule, and this would give me x squared plus some constant c. Right, and this is called an indefinite integral. And one reason it's indefinite is because we're not sure which one we have. Right? X squared plus what? And there's some other characteristics of this. This isn't all of it, but we're just starting out. Right. So if the relationship is that f of x is equal to the derivative of big F of x, then it is true that the original function, big F of x, is equal to the integral of f of x dx. And so this whole process will help you a lot as far as mastering your derivatives. And one of the issues becomes just keeping track of which direction you're going. So I would encourage you to practice a lot of them. Right, so a different example. What is the integral of just dx? And you need to recognize that this was the integral the same as 1 times dx. What has a derivative of 1? Well, the answer to that is x plus any constant. And this would be our answer. Right. A few more, just as examples, and then really I would encourage you to practice. What is the integral of 1 over x to the 5th dx? And so I think about this as x to the negative 5th power. And I know that if I took the derivative of something to the negative 4th power, I would get to the negative 5th. I also know that I would be dropping the negative 4 in terms of the power rule, but my integral lacks a negative 4, which means it must have divided out, so there must have been a constant negative 1/4 here in the first place. I'm going to clean it up just so you can see it nicely. The integral of x to the negative 5 is negative 1/4 x to the negative 4th plus c. And if you're ever not sure, you could always just take the derivative of your answer to check until you grow in confidence. Right. A couple properties to keep in mind. That if you have the integral of some constant times a function, this is equivalent to pulling the constant out and just dealing with the function. And once you take the integral of the function, you'll have your constant times f of x plus c. Another property that probably may seem obvious, but maybe not, is that if you are integrating something f of x plus g of x dx, you can take the integral of each individual piece. This is the integral of f of x dx plus the integral of g of x dx. And a specific example of this might be the integral 4x minus 2 over x plus 5 sine x dx. We can think about this problem in terms of integrating each piece independently. Now typically people won't write this step down. Right? It's not expected that you would show your work in this way, but this is the idea behind what's happening. And if we were to integrate each piece of these, the integral of 4x dx, well, that would have come from x squared. And dropping the 2 times what gave me 4? Well, 2x squared. X to the negative 1, the integral of that is the natural log, so this is the natural log of x, and the negative 2 must have been there already, so minus 2 natural log of x. And the integral of sine, well, the derivative of negative cosine is sine, so it must have been negative 5 cosine x plus c. And one issue with the natural log of x is when you integrate 1 over x, it's always the natural log of the absolute value of x. Right? In a natural log, the argument must be positive. So that's why the need of absolute value. Practice a lot of these.